Hello everyone, welcome back to Altium Academy. I'm your host, Zach Peterson. Today we're going to be talking about the one question that always feels like it's dropping a nuclear weapon on any PCB design conversation, and that is whether or not you should use 90-degree bends in traces. Now, if you're ever reading anything from people pretending to be PCB design experts on social media, or you're reading design guidelines from ChatGPT, you will inevitably see a recommendation to never use 90-degree bends in traces. Should you follow this recommendation, and is it applicable to all designs? That's what we're going to talk about in this video. We're going to look at this conceptually, and we'll look at some simulation results. Let's go ahead and get started. So in this video, we're going to be talking all about right angle traces, specifically from the signal integrity aspect, because frankly, this is one of the biggest signal integrity myths out there that tends to spark debate on social media. So right angle traces, when we have two components, let's say we have IC number 1 and we have some pins, and then we have IC number 2 and we have some pins. How should we route a trace between them? Well, of course, your CAD tool will default to 45-degree traces, where you basically route a trace over this way, you route a trace this way, and then you finish the route going vertically here. So these 45-degree traces are, of course, very nice because they take up a little bit less space than a 90-degree trace. And I think that is one of the main reasons to appreciate 45-degree traces. I can then, of course, fit a lot of 45-degree traces here, just like this, between all of these pins on these ICs. But what about a 90-degree trace? What is the big objection to using 90-degree bends in these traces? Well, the big objection to using 90-degree bends in traces from the signal integrity perspective typically comes from the idea that they are going to create large reflections, or they are going to create large losses due to radiation from the trace. And I've actually seen both myths, but the most common objection to 90-degree traces is that they create huge reflections due to an impedance discontinuity. So here, if we have our trace oriented like this as a 90-degree route, and I send in some signal here in the left-hand side, propagating in this direction, what happens when it reaches this region of the trace? Well, the myth says that we have Z0 right here for our trace, and then we have some other Z out here away from the trace, which we'll call Z free space. And what would we expect to happen when this signal encounters this dashed area here right at this corner of this 90-degree trace? Well, the myth basically says that because Z in free space is very large, we would expect that we get a large reflection equal to basically Z, we'll call it F, minus Z0 divided by ZF plus Z0. And if ZF is much greater than Z0, that would basically take this reflection coefficient to 1. So this is what the myth says, that we get this huge reflection right here at this edge, right here at this 90-degree trace. Now, this is what's really interesting about this myth, is that everybody says this will happen in 90-degree traces, but they never bring up vias. And of course, vias are also a form of a right angle bend for routing in PCBs, and nobody ever brings up this huge reflection in vias, even though it is also a right angle turn. So why do people bring up this very basic misunderstanding about signal propagation along these right angle traces? Well, it comes from this idea that signals propagating along a trace in a PCB are basically like bunches of water flowing through a pipe. And there's this physical picture that, frankly, folks like myself use to teach electricity to 101 level students in university, which helps to understand how current flows in conductors. And that picture is actually not physically accurate, but it is very conceptually useful for understanding Kirchhoff's current law. Now, we need to get away from that when actually looking at how signals propagate on a PCB, because the reality is that signals on a PCB do not propagate like this and then reach a discontinuity and then experience a big reflection as shown here. They actually exist in the space between the conductor and the ground plane in the dielectric that makes up your PCB. So this is not a physically accurate picture because it's based on a physically inaccurate description of how current flows. But now, even if this is not physically accurate, someone will probably say, well, there must be some effect from having this type of shape in a PCB versus a 45-degree bend, or versus even an arced bend like you might see in an RF design. Well, I brought this up in one of my very early podcast discussions with Eric Bogatin, and he described what you might be able to observe in these right angle bends if you have a sensitive enough measurement. Let's take a look at Eric's remarks.
One last thing I want to ask you, and it's probably going to be like dropping a nuclear bomb on the podcast, but there's one last thing I want to ask you, because I want to try and ask all of the very experienced designers this, because it is controversial. What do you think about right angle traces?
Okay, so actually, so at Signal Integrity Journal, we've had a series of articles about this. So the quick answer is folks should go to the SI Journal and type in, I think, corners or right angle bends, and you'll see a series of articles we've had. So the bottom line is, first question is, do 90-degree bends cause signal integrity issues? Or I have to get the right word. Do right angle bends cause reflections? And the answer is absolutely. We can predict them, we can estimate them, we can measure them really easily. The second question is it a problem? And the answer is, unless you're dealing into the 56 gigabits NRZ signals, probably not a problem to worry about. But very noticeable, and we do one of the examples in our class. We have the students build boards with straight lines, with 90-degree bends, and with rounded corners. We have a TDR, and they get to measure them, and then they do an estimate beforehand of what they expect the impact of the corner to be. We estimate the capacitance, and we measure it from the TDR, and darned if they aren't within about 20 or 30% of each other. And that means once you know how to predict it, you can scale it down, and you can ask, okay, when I go to a really narrow line, 50 ohm narrow line, what's going to be the impact of the capacitance in the corner? And it comes out to, 5 mil wide line, you'll have about 20 femtofarads of capacitance. And now you can ask the question, is 20 femtofarads of excess capacitance an important problem in my design? And if the answer is yes, worry about corners. If the answer is no, go on to more important problems. So, but SI Journal is the place to find a series of articles that we've posted there.
So clearly there is some minor effect on the capacitance at this location in this right angle bend. And it's really up to you as the design engineer to determine whether or not that additional capacitance will have a major impact on signal propagation in your specific interconnect. Now what we can do is we can take a look at this from the simulation perspective, because a simulation should be able to tell us whether or not there's going to be a major difference between this type of trace, a trace with 45-degree bends, or even a trace with arced routing, where we make an arc shape here instead of doing a right angle turn. So let's go ahead and jump into Altium. I'm going to show you a simple simulation model that I've built, and then we'll look at some results in Symbior. So now that we've talked about this conceptually and we have an idea of what we might expect to happen at 90-degree bends in traces, let's take a look at a simulation model. So here in Altium, I have 3 different trace routing configurations shown on screen. We have a 90-degree bend, we have a 45-degree bend between 2 points, and then we have a curved trace between 2 points. Now I've done this so that we can create ODB++ files and eventually put these into Symbior, and then we'll do some signal integrity simulations from these trace routing configurations. So the way I've set this up is I basically created a bunch of pads here in the schematic. These pads are all part of a component that then gets imported into the PCB, and then I set up the routing rules and just draw in the routing between these pads to define these interconnects. Here you can see in Symbior, I have the same model brought up, and I've selected all 3 of these nets. And the first thing that we can do inside of Symbior is we can do an impedance check. And all we have to do here is just click run. You can see here what the impedance comes out to, and it comes out to 51.2 ohms. Now that's to be expected because, of course, there is going to be some copper loss that impacts the impedance and causes that impedance to rise above the target value of 50 ohms that we defined in Altium. I talk about that in another video. you can take a look at the link in the description to watch that video. Now, if we expect there to be a large reflection from the right angle bend here on the left side of this model, we should expect the S parameters to be very different for this trace compared to the other two traces. So what we're going to do first is we'll set up a fast SI simulation, and we'll go ahead and set this up to extract the S parameters. Here, I'm just going to go ahead and hit finish. You can see here it runs through and collects all of the measurements, and we can take just a quick look and see what is the return loss at each of these points. So here I'm going to pin this one open, and I'm going to pin the next one open. You can see here that the right angle bend and the 45-degree bends look very similar. Here, when we bring up the arc routing, we can see that it also looks very similar, although it initially appears to have possibly some lower reflection up at the higher frequency range into the 100 gigahertz frequencies. So if we put all of these onto the same graph, we can then really compare these granularly and see which of these has the highest return loss. So here you can see the return loss plot for all three of these trace configurations. It's very clear that the return losses are pretty much at the same magnitude all the way across the frequency range. Now, trace number 3 here is for the arced traces, and it does look like it sits just a little bit lower than the red trace, which is for the right angle trace. So you can see here that the red and the blue have just a little bit of difference up near 100 gigahertz. But aside from that, there really doesn't seem to be much difference in the return loss spectrum. Let's take a look at the insertion loss spectrum. Now here in the insertion loss spectrum, we actually see a lot of difference, and this is really interesting. In the red curve, we have the right angle trace. So the red curve has the largest loss all the way through the entire frequency range. The blue curve is the 45-degree trace, and it has the lowest loss. Here in the middle is the curved trace. So this is where it's the arc routing, and you can see here that it has the moderate amount of loss. Now this is interesting because the conventional wisdom around RF routing is that you need to have these right angle bends in these traces in order to have minimal return loss, and nobody says anything about the insertion loss. But what we actually see is the opposite. The effect seems to be insertion loss driven and not return loss driven. Very interesting. Now you might be asking, why exactly do we see these very slight differences in the insertion loss? You can see here that on this graph, this is not an insertion loss per unit of length. This is a total insertion loss. And if you actually look back here in the model, you can see why that's the case. The right angle turn has the longest length, so it's going to accumulate the most loss. The 45-degree turn has the shortest length, so it should accumulate the shortest loss. And then here, the mid-range length is of course the one with the arc, so it accumulates a moderate amount of loss. So that explains why we get these insertion loss differences, but it doesn't explain why we don't see any difference in the return loss. So if there was going to be a very large impedance deviation right at this point with the right angle turn, we would expect to see a very big difference, not just in the S parameters, but we would also expect to see a very big difference in a TDR plot. So Symbior also gives us the TDR plot. You can see right here we have that result. I'm going to go ahead and bring these up and pin them. So you can see here that when we bring these up, we actually do see a slight difference in the impedance that's encountered along these traces. Eventually, the trace impedance does fall back down closer to the target impedance around 51 ohms when we use the curved trace compared to the 45-degree trace and the right angle trace. So the TDR does seem to indicate that there is a little bit of a benefit in terms of reflections when we're using the curved trace with the arc and the 45-degree traces versus the right angle traces. So this does seem to confirm the myth a little bit, but look at the differences in the impedance values here across these three plots. You can see here that the final impedance at the end of this is only about 0.2 to 0.4 ohms difference. Not a very big difference if you consider what the myth says about right angle routing, which is that you should encounter a brick wall impedance and get these huge reflections that totally destroy signal integrity. If you also look at the peak impedance that is encountered in these three different plots, you see that the peak impedances are all very similar. Here you get up to what looks like about 52.8. This looks like also 52.7 or 52.8, and this one does look a little lower, maybe 52.6, but still not much difference between the impedances encountered along this trace in these TDR plots. Now, all of these simulations were just done using the fast SI algorithm inside of Symbior, but what we can do is set up a 3D simulation inside Symbior. So we're going to go ahead and set that up now. We'll come back in a few minutes and we'll see if all of these results are still consistent in a 3D simulation. And we're back, and we have all of our 3D simulation results that we can look at. So to start, let's take a look at the insertion loss results just to see if we see the same thing that we expect in the previous case, where we should expect the largest loss in the longest interconnect, in this case in the right angle interconnect. So here in the insertion loss plot, you can see that it's a little inconclusive because you do get this waviness that arises in the S parameters, but you can see here that in the red curve, it does reach the lowest dips compared to the green curve and the blue curve. So that does seem to confirm our expectation that we should see larger loss in the longest interconnect, and that's what we see on screen here. Now, what about the return loss plot? Again, if we expect that there is going to be a huge reflection from this 90-degree bend in these traces, we should expect to see that in the return loss plot, and then we should expect to see the corresponding reflection in the TDR plot. Now let's look at the return loss plots. What do we see here? Well, we see what looks like the exact same return loss plot in all three interconnects, essentially just delayed a little bit due to the slight variations in the length of these traces. But overall, the magnitude envelope appears to be the same for all of these interconnects. And what about the TDR plot? The TDR plot also shows different timing, again, as we would expect, because these are time-based plots. We do see that the reflection here from the far end happens latest in the longest interconnect. That's exactly what we would expect. But we see here that the magnitude is essentially the same for all of these. I don't see any difference in the basic signal integrity metrics for any of these traces, whether we have a 90-degree bend, 45-degree bends, or curved bends. Well, I hope this addresses some of the myths around 90-degree bends in traces. Everyone always talks about them as if they are the death of signal integrity, but unfortunately, the results that we've seen from Symbior just don't seem to confirm that. But let me know in the comments what you think. Do you believe the results that you've just seen on screen? And do you have any other evidence that contradicts what we've just seen in simulation? Be sure to let me know in the comments both here on YouTube and on LinkedIn. Thanks for watching this video, everybody. Make sure to hit the like button, hit the subscribe button, leave your comments and questions in the comment section, and of course, don't forget to call your fabricator folks. We'll see you next time.